Good evening, and welcome to HAS members and also to visitors from our North of Scotland sister astronomy clubs, Aberdeen Astronomical Society, Caithness Astronomy Group, Murray's Astronomy Club Sigma, North Ronaldsay Astronomy Group, and Stornoway Astronomical Society. Tonight's timings, immediately after my little introduction, we'll go to the main talk, followed by questions and answers. Around about 8:30, we'll do the club news, astropicks and targets for the month, including the renowned Perseid meteor shower. And probably 10 to 5 to 9, we'll take club member Q&As, and that'll take us to the close. Just to remind you that there won't be any breaks during the meeting, so if you need to leave for any reason, just get up and go and keep yourself connected to the meeting. Now, last month we've been keeping our members and friends updated with emails, Facebook and Instagram links to various astronomy related articles, events and many stunning pictures posted by you over the past month. If you haven't taken the plunge to join Facebook or Instagram yet, have a go. There's a lot of negative nonsense in the press which puts people off, and we keep our pages very up to date. Regarding the observatory, we've still been unable to use our observatory since the lockdown. It's still okay, we check it often. But unfortunately, it looks like we may not be able to publicly use the observatory for some considerable time. We attempted a Zoom solar observing webcast last week, and it was only partially successful. There are quite a few technical hurdles to overcome when webcasting live images, and I need to get a small team of experts together to overcome these. I'm hopeful that we'll be able to do this before the dark sky observing season, and there's an opportunity for all our North of Scotland astronomy clubs and groups to get together and work out some sort of combined webcast observing programme, so we can all benefit from the expertise and enthusiasm that lies amongst us. For your diaries, our next meeting is on Tuesday the 1st of September and will again be hosted via Zoom webinar, and it's looking more likely that this is going to be the way we have to do things for a few more months yet. Anyway, enough from me. I'm now going to introduce our main speaker for tonight, Dr. Mike Peterson. Mike grew up in the Midwestern state of Minnesota, USA, before moving to the northeastern USA for university at a small liberal arts school where he studied physics and music. He then completed his PhD in astronomy at the University of Massachusetts. He moved to Edinburgh in April 2019 to start a postdoc research associate position at the Royal Observatory. It focuses primarily on building high precision computational models of the Milky Way and our most massive satellite, the Large Magellanic Cloud. Very technical looking stuff. So, I had a quick look at Mike's Twitter page earlier today, and it's reassuring to see that there were images from actual real-life observing sessions, including some of our own favourites, the International Space Station, star trails, the Dumbbell Nebula, a comet and open star clusters. Now, just a wee reminder for you all, if you have any questions for Mike, please enter them using the Q&A option, anytime throughout his presentation. We'll gather them up and use them in the discussion session at the end of his talk. It's with great pleasure that I welcome Mike tonight, and here he is to talk about why can't we find dark matter. Over to you, Mike.
Thank you very much for that very kind introduction, Eric. And yes, I am first and foremost, I do love observational astronomy. You should not be intimidated by the title of the talk or the nature of my research. I do really love to get out and do observing, and I'm using my mug from Kitt Peak in Arizona tonight to have a cup of tea while I share this talk with you. So the title of this talk is Why Can't We Find Dark Matter? And it's about the past, present, and future of an intergalactic search. And the key point here is that we think that we have really good observational evidence for dark matter, but we simply don't know what it actually could be. And therefore, we really want to try and tease out what could actually be going on when we look, when we observe the skies. So the first thing that I want to talk to you about is the prologue, and this is the intergalactic search here, and first impress upon you just how hard scientists have been working to actually try and find dark matter since it was discovered. This is just a snapshot of some of the experiments, very large experiments that are taking place in the astronomy community that are really trying to look at dark matter in a variety of different ways. And you can see that there's many different tactics that have been that are being adopted by the community. And I've sort of grouped them into four different boxes here. There are the ones that are primarily driven by physicists, which are waiting in the upper left corner, waiting to intercept dark matter on Earth. There are ones that are in the upper right corner that are looking to find dark matter collisions, either on Earth with the ATLAS experiment and CMS, which are located at CERN under Switzerland, or the Hess telescope that's looking for dark matter collisions that are actually taking place in space. These are collisions of theorized particles that I'll introduce in a little bit. And then on the bottom, we have the more traditional astronomy looks at dark matter. You've got the LIGO observatory that you've probably heard about that looks for gravitational wave signatures. Primarily, it's finding gravitational wave signatures currently from the merger of supermassive black holes, but there are hopes that gravitational waves could be harnessed to tell us something about the search for dark matter. The Planck telescope that you also may have read about is actually trying to observe not dark matter directly, but the indirect effects of the physics of dark matter on what we observe, the structure that we actually observe when you go out and look at galaxies. In the bottom right, we have the real traditional astronomy in the going out and looking at the skies sense. And I've actually been really happy to update this talk recently with the decision to rename the Large Synoptic Survey Telescope, which is a telescope in Chile, after Vera Rubin, who will play a major part in the history of dark matter when we get to that part of the talk. Then this is where we're actually trying to observe the real structure of galaxies and try and figure out just why we observe galaxies where we do. A little closer to home and a little closer to my own research, the European Space Agency has the Gaia satellite that's really trying to observe the motions of stars. So the stars that we see in the sky at night, if you measure them with an extremely high precision telescope that can measure very accurate positions, you can actually see the stars move. And that tells us something, the motion of the stars that we'll see in a little bit tells us something about how much matter and how much mass is actually out there and gives us our first hints about dark matter. So this slide is really just to impress upon you just how hard people are working and just how many different tactics are being taken to try and detect dark matter and give us a little bit more insight about this really puzzling piece of physics. And just to take it a little bit lighter, you may have seen a comic like this before. It's the comic XKCD that's done by Randall Munroe. And I'll just read it here. It asks the question, dark matter density in the solar system is around 0.3 giga-electron volts per centimeter cubed. And we'll talk through these units later. The other person responds, naturally, is that a lot? And the person says, in terms of mass, it means that the Earth contains one squirrel's worth of dark matter at any given time. So if you think about the mass ratio, talking about a squirrel of dark matter to an Earth of Earth mass. person asks, is there any way to find out which squirrel it is? No, it's not literally, but that explains why they weigh enough to set off those spinning bird feeders, and the scientist exasperatedly says dark matter isn't squirrels. But this sort of goes to illustrate to me just how unclear we are about what dark matter actually is. Despite the ubiquity of dark matter and our belief that dark matter really must exist and is the best explanation for all of the scientific evidence that we've gathered so far, it now is surprising, actually, when you find a galaxy that doesn't have dark matter, despite the fact that, again, we don't really know what dark matter is. So this is an article that I just picked out that talks about how remarkable it is when galaxies, when we look up at the skies and scientists point their telescopes at the skies and find these galaxies, how remarkable it is when we detect one that we think doesn't actually have any dark matter. This, of course, naturally leads to the question of what is dark matter? And that's going to be the crux of this talk. I've broken the talk into 3 parts. The first one is going to deal with the history and the observational quote-unquote discovery. And I put it in quotes because I'll leave it to you to determine whether you think that this is convincing or not. So first we have to take a big step back, and some of this is going to be, we're going to try and approach the physics at it fairly gently, but please, please feel free to ask questions going forward about what this might be. So this is a artist's rendition of the solar system from the outside looking in. You can count the planets moving outwards, of course, Mercury, Venus, and then you arrive at Earth. And so I've helpfully tried to annotate it. And what you see when you look at the solar system, if you are to measure how fast each one of the planets is going around the sun, you see that Mercury is going the fastest around the sun. Venus is the next fastest. Earth is going around at about 30 kilometers a second, which remember is very fast. And then Mars and Jupiter and Saturn and so on and so forth. And we still count Pluto, at least in the context of this, because it gives us another far out data point to look at the speed as a function of distance. And the shape of this curve is going to be important. So you don't need to memorize any of the numbers or really take too much away from this graph, but the point is that in the solar system, what we observe is that when things are close to the sun, they move very quickly. When things are far from the sun, they move very slowly. And this has been very successfully shown repeatedly, and this was first formulated by Isaac Newton, who was born in 1643, and he formulated this theory of gravity. And really the underpinning of all of this is that gravity, for better or for worse, is the ultimate unseen influence. And so we are often stuck conjecturing and describing gravity without a really firm grasp of what we're actually talking about, or what is actually causing the effects that we observe. But that said, gravity has been used to great effect. Newton's gravity has been used to great effect, to the point where one of my favorite examples is that in the 1800s, Urbain Le Verrier was able to actually predict where Neptune would be because of very precise gravitational calculations, figuring out what was actually happening with the asteroid belt. So again, remembering that this curve starts very high towards the center and very low towards the outskirts, we can then take a step out, and I'm hoping you've seen this image before. It's really stunning, coming out of the Gaia satellite. And what this is this is an unwrapping of the sky. So if you were able to see the entire sky at once, the whole sphere, and then you reprojected it onto one image, so you unwrap it sort of like you're peeling an orange in one go. And what you see is you see the whole sky. You see I've annotated where the galactic center is, which happens to be directly in the center. The image, and because we're looking at this from the perspective of Earth, or very near about Earth, you're seeing this is from the Gaia satellite, so you're seeing this from far above Earth, actually. But because you're seeing that, you're actually seeing the whole disk of our galaxy, our spiral galaxy, that cuts across the center of the plane of the sky here. That's been oriented so that it cuts across the center. And I'm hopeful that you've at least had some nice dark nights where you've been able to see the milky line of the galaxy arcing across the sky, and the galactic center is a favorite target of mine to try and look for the ambient glow. You can see it in the constellation of Sagittarius. One of the most striking features in here, just as an aside for myself, is unfortunately not visible from the northern hemisphere, and those are the large and small Magellanic Clouds, which are these bright clouds in the lower right corner. You've got two striking galaxies in here if you ever get a chance to go to the southern hemisphere, or if you've been to the southern hemisphere, I'm really hopeful that you got a clear night and were able to see those. They're really stunning to see with just the naked eye. But again, this is what our galaxy looks like if you're looking out from Earth. What we really want to be able to do, though, is to make that same figure plot that we made of distance from the center versus speed that we were able to make for the galaxy, or for the solar system rather. And so for that, we want to take a step back and look at another galaxy that we think looks something like the Milky Way. So I've put Earth in quotes here because this is Hubble's view of the galaxy named NGC 5754, which many people think is a nice analog for the Milky Way. So if we were able to zoom way out from the Milky Way, we had a satellite that could get out of the galaxy, we theorize that the Milky Way would look something like this galaxy. And I've shown you approximately where Earth would appear in the case where this actually was the Milky Way. Earth would appear sort of in one of these arms, a little ways out from the center of the galaxy, 8 kiloparsecs to be precise. When you look at these galaxies and you measure the speed as a function of the distance from the center, so we're seeing the same axes that we saw in the plot before, and you ask what the speed is doing as a function of distance, what you see is not the curve that we expect, the dashed red curve that starts high and ends low as you get to larger distances, but you see something that starts low and ends high, confusingly, when you measure this as distance from the galactic center. And people have called this is the rotation curve, approximately this radius, 8 kiloparsecs. So while from naive gravity or Newton's gravity, we would expect Earth's rotation speed to be somewhere down here, somewhere down low on the red curve, what we actually would observe is that Earth, and what we do actually observe in the Milky Way, is that it's much higher, and it's orbiting the center of the Milky Way at about 220 kilometers a second. The striking characteristic that you should take away from this figure is that what you see is that apart from the very center, at small distances from the galactic center, where the rotation curve or the speed is rapidly rising, it's actually flat. So it's not a strong function of distance, but these curves are relatively constant the further you get from the galactic center. Now, this is really puzzling, and the best way to explain this is by saying that there's actually a lot of extra matter that you can't see that's causing extra gravitational pull and keeping those stars orbiting the center of the Milky Way or the center of the galaxy very quickly. And this is what we call the flat rotation curve. And this was a discovery that was first made in the late 1970s. You can see the date on this paper from the Astrophysical Journal, where Vera Rubin publishes the first bombshell here of the measurements of the speed as a function of the distance from the galactic center in this fairly dryly titled extended rotation curves of high luminosity spiral galaxies. But what's actually buried in this is the figure that I just showed you that shows you that rotation curves are flat. There must be more mass there than we think. So it's not centrally concentrated like in the solar system, where you've got the sun at the center and very little mass elsewhere in the solar system. But instead, in the galaxy, you don't have a highly concentrated center. You have mass sort of at every radius. And a lot of this can't be seen if you just count up how much mass there is in the stars that you can observe. Now, I just want to note also that Vera Rubin has been recognized recently for her contributions and this massive contribution to the astronomical literature. And I mentioned this at the very beginning, but just to reiterate, there's a telescope being built in Chile that is one of the real state-of-the-art telescopes that's going to give astronomers a real jump into the future and a real much more information about dark matter and about many other things in astronomy as well. And here's Vera Rubin at a telescope in Arizona, looking at the camera. And this is in the late 60s. And so you can read the specs for the Rubin Observatory, and you can visit the website. There's a lot of good outreach information there if you'd like to learn more about that project. But this is going to continue on this great tradition of discovery of dark matter. Now, of course, since galaxies are everywhere, one might also think that this exists on larger and larger scales. So here's a giant zoom out. So before I showed you just a snapshot of the galaxy, but now the Milky Way is just a single point in the very center of this. And these are all the galaxies that are, and I'll put large air quotes on this, very nearby, because they're about 100 million. This image is about 100 million light years across. Of course, this is an artist rendition. Since galaxies are everywhere, what we can also determine, and you can see that they seem to show these properties where you see these big clusters of galaxies, like the Fornax cluster or the Virgo cluster. And if you look at these on a different scale, you can actually see this sort of bothered this astronomer, Fritz Zwicky, who thought, why are all of these galaxies clustered on different scales? Perhaps there's some unseen mass that's drawing them together. And he actually predicted the existence of dark matter without significant evidence at the time, nothing as firm as the rotation curves of Vera Rubin. And if you're looking for a book, there is a new biography of him that came out last year that describes a very interesting scientific life. But getting back to the clusters and why Fritz Zwicky thought that there must be extra matter there, he didn't have anything like this. Of course, this is very nice optical data from Hubble. But what we're seeing here is that you can see these clusters if you actually zoom in. And of course, this is a real image that came from Hubble. And what you're seeing here is each one of these is a galaxy. So with the exception of these points that show spikes, this is an actual galaxy. And we've zoomed in a little bit from where we were before. This is just 3 million light years across in this image. And each one of these is a galaxy, and you could go and measure the rotation curve for each one of these. But instead of measuring the rotation curve for each one of these, we can look for another piece of evidence about dark matter, and that is simply examining the clustering and trying to figure out whether there's extra mass in this cluster more than we would have predicted. And for that, we actually have to turn away from optical data. We've basically been using optical data so far, but now we'll step aside and look at what else we can see in this. And you see some really funny things that don't actually look like galaxies. So you've got these really long stretched images, and one might naturally wonder, well, what are these actually? And this is something that's been predicted, and we'll talk exactly about what it is, but it's actually the distortion of galaxies that are located far behind this cluster. But just like using a magnifying glass, the mass of the cluster is so massive. For instance, in this particular case, we're talking about something that's 150 trillion times the mass of the sun. Just like a magnifying glass or your glasses, this will warp the galaxies and change them into different shapes than you actually see, than they actually are located far behind this cluster. So this is an image that we see the optical data, but now I've overlaid what the hot X-ray data from the Chandra X-ray telescope in pink, and the radio emission from NRAO, which is the National Radio Astronomical Observatory, in blue. And so what you can see is that there's a lot of mass in here, much more, but then is just in the galaxies, and it's actually interspersed between all of these. And the hot X-rays tell you something about just how much mass there is, because you need a huge amount of mass in order to reach temperatures hot enough to excite X-rays. So while we look at these galaxies and we see individual galaxies as these collections of light, when you look in radio emission or in X-ray emission, what you see is that they're actually all sitting in one large structure that's all held together by some large amount of unseen mass. And that's where the problem continues to deepen. There's all of this mass that's sitting out there that we can't actually explain, that we can't see. When we take an optical image, it's not visible to us. The effect is extra obvious when you look in in colliding galaxy clusters. So when you have two of those clusters that have crashed into each other, you can see hot gas and a lot of extra mass as indicated by the radio observations. You can see that these collisions have taken place and you're left with hot gas in places that there isn't actually a galaxy. So while the stars have moved comfortably through each other, the galaxies have passed by one another, the extra mass has collided and become stuck. And so you can see all of this extra mass that isn't actually light, isn't emitting any light. And so while we see the effect of the gravity from these, we don't see any light from them, hence dark matter. And this naturally led scientists to wonder whether we should change our understanding of gravity. So we have a picture of Newton here, and the natural question is, well, maybe, or the natural thought rather is, well, maybe Newton's actually wrong and we should modify it. But I would say not so fast. We have another couple of sections of this talk, and I'll try and explain where we're at the forefront right now. And this is part 2, the theoretical frontiers. Don't be scared by the particle physics nature of this, which is talking about the actual theory for what dark matter really could be. So I hope that I've convinced you in the first part of this talk that we've got this grand mystery. But there's been parallel work taking place really since James Clerk Maxwell, who has a nice statue in Edinburgh, if you've seen it before, who in 1865 published this other dryly titled book, A Dynamical Theory of the Electromagnetic Field, and ushered in this new era of actually trying to explain large-scale physical effects like electricity by explaining them with small particles that carry the information. So after this prediction in the 1860s, electrons, protons, photons, and neutrons were discovered in the following 60 years or so. But that wasn't enough, because that just explains electromagnetism. So then people began to look for particles to explain many other physical phenomena, chiefly among those a particle that could be theorized to carry gravity, and explain that. And this is where I have to introduce a mass scale. And this is a ruler that you can think of that will tell us where, that if you encode the mass on this from everything in the universe, where they actually fall from end to end. And at the low end, we're talking about something that Einstein described, which is this famous E equals mc squared. We're describing things in electron volts, which just means that we're weighing things using electricity instead of the traditional kilograms that we normally would think in. So let's give ourselves a little bit of a scale here. So humans here are somewhere around, this is very rough. Astronomers like to think in orders of magnitude, so that's a good thing to do. So in 1932, after some of the first particles have been discovered that Maxwell theorized, we're talking about, we've got humans here, something like pollen gets down to nanograms, but then everything below that is orders and orders of magnitude smaller than that, much, much lighter. Protons, neutrons, electrons, and photons are almost unimaginably light. On the other end of the scale, before we get to full-scale galaxies, we've got the sun sitting at roughly 10 to the 30 kilograms. So that's 10 followed by 30 zeros. A little bit later in the, just after most of those particles had been discovered, Paul Dirac came out, another famous scientist, with the quantum theory of the electron, and this ushered in even more particles. None of these, of course, describe gravity. Still, these are even more fundamental particles that describe the makeup of protons, neutrons, and electrons, and some of the more exotic physics out there. So while we're making great progress here and up till the 1980s describing these very detailed physical processes, we're having a little bit more trouble explaining the simple fundamental process that Newton observed in the 1600s. So in 1984, we were able to update the mass scale, or circa 1984. You can put in the mass scale. Here's the standard model, all of these exotic, these different exotic particles in here. And you can see that we've slotted in neutrinos now onto the mass scale. And that led to even more desire to hunt for particles. And this is really where the dark matter search has really begun to heat up. Things like the Large Hadron Collider, which is at CERN underneath Switzerland. There's a plan in the 1980s to probe even more of these mass ranges and look for more particles that we haven't found yet, hopefully find something that looks like dark matter and can explain all of these confusing observations that have been taking place since Fritz Zwicky proposed dark matter in the 1930s and Vera Rubin discovered it in the late 70s. The theory here is that you would look in a different mass range, and the thought behind the Large Hadron Collider is that you look at the low mass scale because that's where we think that most of these particles are going to live. So the most massive particles that we've found so far are the protons and neutrons. You can probe up to this with the ATLAS and CMS experiments, which are two of the ones that I introduced at the very beginning. The thought here being that in the center, I've labeled this thing as the sort of can't miss range, which is where you can't be confused. These are things that you can see either by eye or simply with regular microscopes. So if dark matter was one of those size scales, for instance, if dark matter was the size of pollen, we would have seen it already. You can also hide things on the more massive end, and we'll get to that in a second. So after the theory of trying to build the Large Hadron Collider in the 1980s, it actually was realized, and it's very much operational now, and there are plans to hopefully expand it. Spoiler alert, we haven't discovered dark matter, and so the plan is to try and extend this further to look in even larger particle ranges. So what's actually happening in these? Very briefly, very simply, you send particles in, you let them crash into each other, and you look to see whether some of these, whether the mass that's come out is the same as the mass that went in. If the mass that came out is different, then you've found a new particle. And this is actually the way that Scotland and Edinburgh again figure into this large puzzle, which was, you may have heard of the Higgs boson, discovered, theorized originally by Peter Higgs, who was born in 1929. So you can see that this is a contemporary work that's taking place. He theorized this in the 60s and 70s, and then in 2012, with the advent of even higher energies that the Large Hadron Collider could reach, the Higgs boson is actually discovered. So we're doing a great job on the theory, except for a couple things, which was that where the Higgs boson was predicted to be was not actually where it was found. So this has led to great consternation in terms of searching for dark matter as a particle that we think that we could find. If we could be off by a factor of 100 in where we're looking, then this is going to be a very hard search indeed. And just to give you a sense of how precise these experiments must be in order to actually detect these particles, what you're seeing on the right panel here is that this little bump is actually the detection of the Higgs boson. So we're looking for these tiny little bumps against this giant sea of background in the detectors. So you're looking for something very faint. So it's really easy to imagine how we could just be continuing to miss this when we're looking for these particles. So again, we can come back to our mass scale, and this is where we're at right now, circa 2020. The Higgs particle slots in here right around a GeV, or a giga electron volt. So this is actually the new most massive particle, more massive than the protons and neutrons. But again, it still falls below this maximum energy that we could reach with the Large Hadron Collider. And this is where we're going to start to wonder, well, are we actually looking in the wrong place? But there's another scientist who proposed in the early 1900s that the mathematics really suggests that there should be many more undiscovered particles. So yes, we should keep pushing ourselves to look for these particles, even though we haven't had a lot of success with them yet. And this is where the real present-day search of dark matter has taken us. And this is where I'm going to divide things in half here. So while I described the things that you can miss on the low end of the mass scale, so the light mass here, the lighter masses on the left, that's up to the physicists. And you can see I've annotated this at the bottom. On the right side, where things are more massive than humans, sort of in the mass range of the sun, in this chasm where I haven't really described too much, those are called the machos. And I really appreciate this branding. And I wish I could tell you that they weren't acronyms and it's just come up with, these are just clever names that astronomers came up with to win the nomenclature battle of machos versus wimps. But no, they actually stand for detailed things. They just happened to work out in such a way that you might want to be on the astronomy side of this. So WIMPs stands for weakly interacting massive particles, and that's everything that we've been describing so far. All these low mass particles, these are interacting massive, quote unquote, particles, maybe something in the mass range of the Higgs boson. On the other side of things, if you go to the more massive side, we're talking about the massive, and this real liberties were taken with the acronyms here, compact halo objects, and these would be things on the more massive scales, and that's where you have to start to get a little creative. And that's where I'll show you that this energy scale actually came from another XKCD comic by Randall Munroe, and he's got many proposals, mostly unserious in this. Please remember that this part of the talk is a comic. Theories about dark matter candidates, and this should tell you something about just how unsure we are. We still have to look in this entire mass range to try and find things that can explain the dark matter observations. And here's sort of where we're at. Some of these have more and more exotic names. So we've got axions, we have sterile neutrinos, neutralinos, and Q-balls are all particles that have been proposed that might fit within the standard model that I described before. On the far side, where it's up to astronomers with machos, there are things that the main thing that we think that we're looking for is actually black holes. But the problem is, you can see in these hatched regions that they've actually mostly been ruled out by different aspects of the astronomy. So this is where I'll bring in the theory, all of the different experiments. You can start to try and to put together the prologue and this part of the talk and where all of these experiments go. So physicists here, again, on the left, there's plenty of experiments over there. Astronomers on the right are using these observations to try and find things like gamma rays that would be emitted by black holes if there were just enough black holes dotting the night sky to make up this mass. I will just do a very brief aside about black holes and invite questions if people want to ask about them later. The main reason that they're ruled out is actually the very powerful gravitational wave observatory LIGO that's actually detecting these different masses of black holes. In order to have black holes actually be the constituent matter for dark matter, or describe dark matter, or explain all of the observations, they would either have to be much more massive than this or much less massive than this. So we're stuck with things sort of in this no man's land. LIGO is actually, the discoveries from LIGO have actually been very surprising, the mass range that these black holes were detected at, because the vast majority of them are detected in what was previously thought to be sort of a dead zone between 5 and 30 solar masses for black holes. So again, the scale here of black holes is in solar masses, so multiples of the sun. The bottom line is that given all these experiments that I showed you on the last slide and in the prologue, we still haven't found any evidence for black holes being dark matter. So that leads us to the main point of part 2 of the talk, which is questioning, well, maybe we should actually give up on particle physics. So in part 1, we asked, should we give up on gravity? In part 2, we asked, should we give up on particle physics? And this is where I'm going to leave you with sort of a part 3 here, which feels a little anticlimactic, but it's sort of teasing where we're actually trying to go from here. And I would argue that there's 3 main ways that we can do this, that we can proceed from here. And progress is being made on all 3 of these fronts. We can either try to improve our observations to give ourselves to, well, we should try and do all of these 3 things. We should try to improve our observations, should try to improve the models that we have to explain dark matter, and then we should also improve the theories that sort of underpin all of this. And so I've described in parts 1 and 2. In part 1, you're really trying to improve the observations to get a handle on what the problem is. In part 3 and part 2, in part 3, we're trying to improve the theories, try and figure out what actually could make up dark matter. And then this part, the part that's closest to my heart, is how to improve the models. So again, bringing back the Gaia observations, there's another thing you can do to look at the whole sky to improve your observations. And this is something that really would have helped Fritz Zwicky and Vera Rubin earlier on, which you can use the Planck satellite instead, which measures the temperature of the sky very precisely. So while we look at the sky and between the stars, we see blank darkness, what's actually there actually is, if we had eyes that could see radio waves, you would actually see what looks to be the static on a television. So this is the galactic center. I've again marked the galactic center on here. This is the map that you would see. And it's basically what astronomers would call a noise pattern, meaning there isn't really any structure in this. But there's information in the noise pattern, and what the information tells you is that no, actually 26.8% of all the mass in the universe still has to be dark matter. Everything that we can see, all the stars, all the comets, all the planets, everything that we really like seeing when we go out in the backyard is in this just 4.9%. And you'll have to get someone else or invite me back to talk to you about dark energy, which I know when I show you this slide and you see that it's 70% of the mass budget of the universe, you might ask why I'm not talking about that, but we'll save that talk for another day. So again, roughly 27% of the universe is dark matter. We can try and do things like actually improve our models. And this is where we get to sort of state-of-the-art simulations, the type of things that I do most of my research on. This is the Illustris simulation, which has this lofty title of trying to get to a predictive theory of galaxy formation. And while they show you the stars in all the press releases, what you actually need to make these models go is you actually have to have dark matter underpinning all of the stars. So now I've peeled away the layer of stars and shown you all the dark matter density. So in pink here on the right side, you're seeing high dense regions of dark matter. And you can see that the dark matter in these simulations looks like what we saw in the cluster images before, where the dark matter is just pervasive and fills the voids between all of the galaxies. You can see what, if we were able to see dark matter, this is what we expect the night sky would look like. You would see fantastic streams of dark matter, maybe even things that looked sort of like dark matter stars. This is if we zoom out. So before we were much zoomed in, I was showing you the little box, and then you can zoom out. You can see that there are these vast tendrils that span the entire sky of dark matter that would connect every galaxy to other galaxies. And I'll just briefly talk about my humble contribution to this, which is trying to make predictions for the dark matter experiments that are actually on Earth. So this is a paper that I wrote a few years ago now that is probably ready to be updated while I was working on, I wrote this while I was working on my PhD. And this describes the actual measurements that you would try to make on Earth with those experiments that the physicists are doing. But I came at this trying to inform it from the astronomy, trying to build the best model possible for the Milky Way, and ask what you actually observe in this model if you pretended that you were on Earth in it. I'm happy to answer more questions about that. The last part of this, the last thing that I said there, so that was 1 and 2 on what we can improve the observations, and we can also try to improve the models. And a question mark would be improving the theories. And I'll tell you that there are tons of people working on this. This is a snapshot of just a week, roughly at the end of last year, where people are posting papers and papers, or writing papers and papers with new theories for what dark matter could be. And we're really, as scientists, sifting through all of these and trying to figure out what model best explains all of the observations. So I would argue that this is really a fundamental scientific process here. We're trying to do 3 things. We're trying to improve our observations, we're trying to improve our models, we're trying to improve our theories, and we're just going to continue iterating on this, trying to solve this giant cosmic mystery. And we'll keep iterating until we find dark matter, or until we disprove the observations that seem to show that dark matter exists. So I hope that I've convinced you over the course of this talk, again, that there's ample evidence for dark matter. There's good reason from particle physics and fundamental physics to think that that there actually should be dark matter out there, but we simply cannot find it. And scientists are working as hard as we can on many different fronts to actually try and detect dark matter. We're just not there yet. Thank you.
Very good. Thank you very much indeed, Michael. That's tremendous. I've got some questions for you. Can you hear me okay?
I can hear you just fine.
Okie doke. Just half a dozen. You'll be fine. This is a straightforward one. First, from our David Davidson, Surely just by area and diameter, most of the galaxy mass is in the outer regions anyway. So why bother with dark matter?
That is true. So while the curve for the galaxy doesn't look exactly like the curve that you saw for the solar system, where all of the mass from the solar system is essentially all of the mass from the solar system is concentrated at the center. Galaxies still have that as well. So if you were to make the same plot of speed as a function from the galactic center, you wouldn't see that fall off. You would actually see or you would expect to see that same fall off that you see in the solar system. Now, even if that's not convincing, if you go and look at far beyond the outskirts of the Milky Way disk, so the Milky Way disk extends to roughly 30 kiloparsecs. If you double that and look at 60 kiloparsecs and you find stars out there, they're still moving at that same 220 kilometers a second, even though you don't see any real stars out there, any other stars out there.
Okay, let's go by that one. I've got one that is very similar, and that is from Eric. Is there some lens correction calculation that you can use when you analyze these very distant galaxies that appear distorted?
That's actually exactly what you do. So in order to figure out the mass of the clusters, there are fairly simple lens equations, just like the equations that you might have done in physics, where you write down how light travels through glasses or through magnifying glasses. Just like that, you can write down the same equations for how the light is bent around the clusters, and that's how you end up with those very long, skinny streamer galaxies that are really distorted.
Okie dokie. One question from myself. What is your personal favorite as the constituent of dark matter, and why?
I'm very cognizant of the fact that this is being recorded, and so I'm now very much going to be on the record. But I will say that I think that the particle physics is the most convincing to me. So I think that the story that I told about the Higgs boson, where we thought it was going to be one place, and then it was 100 times more massive, I think we're going to find something similar to that, where we're looking in one place for the particles, and it's going to turn out to be 100 times different than that, but still in sort of that weakly interacting massive particle range.
Okay, thank you for that. Another one from Eric. You refer to Newtonian physics as the method of calculation. Is there a role for quantum physics?
There is a role for quantum physics. For the most part, quantum physics takes place at the very small scale. So what makes gravity so remarkable is that gravity has basically infinite effects. So no matter how far away you are from something, you still feel gravitational effects. For quantum physics, they tend to take place on very small scales. So mostly the size scales of the atoms or the constituent parts. So depending upon what makes up the physics, what makes up the particle nature, if we assume that it's going to be particles of dark matter, then quantum physics might play a very large role in all of this. But another reason that I said Newtonian physics is because there's actually competing theories of gravity that aren't Newtonian. They're mostly modified versions of Newtonian, with the prevailing one being Milgramian dynamics, which has just a modification to the structure of Newton's equations.
Okay, thank you for that. I'm going to come back to a question from Eric. I think this time I'll go to Rich from Sigma. Is there any role for amateur observers and astronomers in this field?
There is actually, and there are things there are things that we need to do to be fairly clever. But part of one of the major dark matter theories. So I'm just trying to formulate the full thought here. So I described the dark matter theories that are more massive than the can't miss scale, the machos. And so on that side, if you start to see things, then you start to see different things being deflected in unexpected ways, large scale things. So for instance, the orbits of comets will actually be changed if you have more massive dark matter particles or dark matter objects. So what astronomers actually need are things like variable light curves, where you're trying to figure out how things change with time, because how things change with time on these medium scales can help us to rule out or to help us to rule in what dark matter actually could be on the medium size scales. So the Large Synoptic or the Vera Rubin telescope is actually trying to determine how things change with time. But the real reason that that's taken place is because amateur astronomers have been amazing at taking observations of how things locally change with time. So you can look at how stars change with time. You can look at how asteroids change with time and the orbits of asteroids. And how all of those orbits work will tell you something about any extra unseen mass in the solar system that we can't explain.
Okie doke, thank you for that. A question just popped in from Mick O'Donnell. Does dark matter or even dark energy affect the solar winds that bring the aurorae at the Earth's poles?
For the most part, no, because we're talking mostly about massive size scales here. So dark matter is most effective on the largest scales. Remember the original comic that said that the rough proportion is that there's about a squirrel's worth of dark mass on Earth, or so, if you believe that. Dark energy is a little bit more interesting because it has to do with how the actual fabric of the universe is expanding or changing with time. So over billions of years, you would see a difference in the aurorae, but over the course of our lifetimes, the effect is far too small for us to see.
All right. Thanks for that. A last question then from myself. You mentioned modified Newtonian gravity and that sort of thing. How probable is it that we're simply misinterpreting how gravity works on the grand scale?
I left plenty of room for that to be the case, which was the takeaway from part one was, well, maybe we should revisit gravity. And while the rest of the talk really asked, well, maybe we should revisit particle physics, or maybe we're missing something in the fundamental physics here, we shouldn't discount that our fundamental theory of gravity on these most massive scales may not be correct. Mm-hmm. That said, every theory that we scientists have thrown at the observations for what gravity could be that isn't Newtonian, they've all failed. So it might be that we're not being clever enough, but people have worked quite hard to determine what else could be happening with gravity, and they haven't had any success yet.
Excellent. Thanks, Mike. I'm going to hand back now to Eric, if I may, and he'll take us forward from there. Thanks.
This opportunity to thank you formally for a most interesting and thought-provoking talk. Normally, Mike, you'd be receiving a token of our appreciation and a thank you card designed and printed by Pauline. And you still will receive these things, except we'll need to get some contact details and work out a way of getting them to you. We'll talk about that after the meeting closes. But Mike, thank you very, very much once again.
Thank you. My pleasure.
And now we go over to our club news, astro picks and targets for the month. Pauline is back with us this month and has another wonderful presentation for you, including information about observing the forthcoming Perseid meteor shower. Over to you, Pauline.
Okay, right. hopefully you can all hear me now, and we'll try again. Right, the constellation this month is Aquila the Eagle, and the constellation itself fits rather nicely into the eagle shape with his wings outstretched and his nice long tail. But be aware that not all drawings of the constellation seem to fit the eagle shape at all. In fact, some of these don't look in the least bit like an eagle. Aquila tends to be found in our southern sky, and you can see that the Milky Way passes directly through it. In Greek mythology, Aquila, the eagle, represents the bird or the eagle that carries Zeus's thunderbolts. But if we have a look at a Greek coin, although we've got Zeus and the eagle here, he's not carrying the thunderbolts. We have to go to Egypt in order to see the thunderbolts actually grasped in his claws. And the story, and there of course there are always a few stories, suggests that Zeus sent an eagle, or quite possibly turned himself into an eagle, and kidnapped Ganymede the shepherd boy in order to be cupbearer to the gods. Now, Altair is the brightest star in Aquila, and Altair forms one of the 3 stars of the summer triangle. The others are Deneb in Cygnus and Vega in Lyra. So of course Altair is the southernmost of the sky, of the summer triangle. Altair has a magnitude of 0.76. And that's pretty bright, so we can see it quite easily, and it's the 12th brightest star in the sky. It's about 16.8 light years from Earth, so it's one of our closest naked eye stars, which is one of the reasons why it is nice and bright and easy to see. It rotates in just 9 hours. It has a very rapid rotation rate, whereas our sun, in comparison, rotates in 25 days. So Altair's fast rotation rate gives it this lobate appearance. So it's flattened at the poles and it's much wider at the equator. And this, in fact, is what Jupiter looks like. It also has a lobate appearance. Now, when you're looking at Altair, if you look up and slightly to the right, you can see another star, which is called Tarazed. It's a couple of magnitudes fainter than Altair, and it's an orange giant, so sometimes it'll look slightly orangey. You should be able to see this star quite easily, as long as you haven't got an awful lot of light pollution. But I use it as a marker, if you like, if I'm looking for Altair. Because sometimes if I'm in unfamiliar territory, or there's some cloud in the sky, and I'm wondering, am I actually looking at Altair, then Tarazed is actually quite a nice star to find, because it tells me that, yes, I am. However, the other star on the below Altair, called Alshane, is much fainter. It's a whole magnitude fainter than Tarazed. And if there's any light pollution around, or if the moon is bright, you're not going to see it. And the other stars within the constellation are all of a similar magnitude, from 3 to 3.5. But this is the interesting one. This is Eta, and it's a variable star. And it varies between magnitude 3.5 and 4.4, and it does this in a week. And Delta is a very useful comparison star, because it's virtually the same magnitude as Eta. So while you're watching Delta, you can see Eta gradually fade and then come back to the same or very similar magnitude to Delta. So it's a good variable star to start off with. Being in the Milky Way, there are a number of deep sky objects. Unfortunately, most of these deep sky objects are too faint to be able to see unless you've got a large telescope, because they're magnitude 11 or 12. However, there are 3 binocular objects. So here we have some dark nebulae, and these are areas that are full of dust, and that these dusty areas obscure the stars from behind, and the Milky Way is full of dusty regions. But these 2 in particular, Barnard 143 and 142, are nice and small and separate. You'll need binoculars to find, first of all, find Altair, then find Tara Z, and then move over a little bit to the right, and you should come across Barnard 143 and 142. And together, they look like an E, which is why they are called Barnard's E. And this, by the way, is Tara Z. Now, you don't need to see the Milky Way in order to find the dark nebula. If you've got binoculars, just find Tara Z and then pan across, and you should come to these dark nebulae. Of course, there's a lot of light pollution, or the sun or the moon is really bright. You will have difficulty. So a dark sky is best. And that really goes for most of the stars, and certainly the variable star within Aquila. The other couple of objects that you can see are open star clusters. There's one here, and there's one here. So this is 6709. Start with Zeta with your binoculars, and then pan down in a diagonal line near enough. Because you're in the Milky Way, there will be other star clusters like this one, but it's not nearly so easily seen as the 6709. And this is it. It's supposed to have a diamond shape. You need your imagination slightly. There are roughly 40 stars, an overall magnitude of 6.5, so it should be easy to see in binoculars. And then we have 6755. So this time start with delta and move across very slightly up, and you'll come to this open star cluster, which is a lot more widespread, but it's still quite a nice cluster to look at. 7.5 magnitude, it should be visible in binoculars. And don't worry, I will compile all of this and put it into a document and send it over to you. I've got a couple of planetary nebulae to look at because they're pretty and they were photographed by Hubble. So here we have the Phantom Streak Nebula, which is here. And then we have got 6751, which is called the Glowing Eye Nebula. And if that wasn't good enough, it's also known as the Dandelion Puffball Nebula, which has to be my most favorite name of any planetary nebulae there are. The claim to fame that Aquila has is that it could contain the largest single mass concentration of galaxies, making it the most massive structure in the universe. And it's called the Hercules Corona Borealis Great Wall. This is a photograph taken by Hubble. In fact, it's 18 photographs stitched together, and you are looking at all these superclusters, which of course is what Michael was mentioning. And this is just what they think the large-scale structure of the universe looks like. This is the immediate vicinity. And once again, all these that you see here, every single speck is a supercluster, or is a cluster of galaxies, and then these are arranged together in superclusters. So this is where we are, right in the middle, within the Virgo supercluster. Aquila is in that direction, and here we have the Hercules supercluster and the Corona Borealis supercluster forming this enormous wall. But there are walls of superclusters all over the place. And within these walls are these huge voids. And as I said, this is what the large-scale structure of the universe looks like. So if we now go on to what we can see in the sky, If you look at Aquila here, then just below we have got Jupiter and Saturn. Now, if you're not sure where Aquila is, it's very easy to find Jupiter. It's shining at magnitude minus 2.7 at the moment, so it is in fact extremely bright. Just look up and you will come to Aquila quite nicely. It's a little bit higher, well, Aquila is a little bit higher in the sky than you might expect. And this cross here is, or marks, the zenith, which is the point directly above you. And if you want to try and look at Vega, you will end up with a crick in your neck because it is virtually directly above you. And of course, where you've got Jupiter, you can easily find Saturn. And this is a photograph taken by Michael O'Donnell of Saturn and Jupiter. Absolutely fabulous photograph, showing them off really quite nicely. Now, it is possible to see all the planets in one night. Not all at the same time, but all separately, although you can see some of them at the same time. So of course we start off with Saturn and Jupiter. They rise at about 10 o'clock at night. They remain fairly low all the way along. The moon interfered on the 1st and 2nd of August, but last night it was around here, so it's now well out of the way of Jupiter and Saturn. The next planet to rise is Neptune, but you will need a telescope in order to be able to see it. Mars rises at around 11 or so. Wait a couple of hours until it gets higher in the sky. It should begin to look nice and red, and it shines at a magnitude of minus 1.4, so it's brighter than Saturn. And Mars is going to get brighter, and its size is going to get bigger, or its apparent size, I should say, is going to get bigger as it leads up to its opposition in October. And that simply means that you have Mars, Earth, and the Sun in a line, and Mars is at its closest point to Earth. And I'll say something else about that a little bit later. After Mars, we have Uranus. Again, you should really use a telescope. But if you know where to look and the sky is dark enough, you could use binoculars to find it. Venus rises at around maybe 2 or so in the morning. It's dazzling at minus 4.5. And it's very easy. You can't miss it. It's very easy to see. Mercury rises a little bit, well, a couple of hours after that. It's brighter than Saturn, but because it is so low down, it's not going to get much higher. It's in the twilight, early morning glare that the chances of seeing it are really quite slim. If you've got a very clear, low eastern horizon, it's possible, but for goodness sake, the sun isn't far behind, so if you use binoculars, be really, really careful. Now, who has managed to see the comet? Maybe you could raise your hand or put something in the chat box so that we can find out. I saw it 2.5 weeks or so ago, and it was absolutely vertical, head down, tail up. It took me until about 1:45 to find it with binoculars, but it was well worth the wait. That was the time when it became dark enough to be able to see it. It has now passed its closest point to Earth, and it's gradually moving away. So it's getting fainter and fainter. It's in Coma Berenices at the moment, but it's much more difficult to see. This is a photograph taken by Dave on the 12th of July. A beautiful image, and we've got more of these to show you. And then the big thing that's happening this month is the Perseid meteor shower. Now, the Perseids are visible from middle of July to late August. It's a shower that is caused by the comet Swift-Tuttle, which has a 133-year period, but of course it has left a trail of dust behind. So every time Earth orbits the sun, it'll pass through that trail of dust and the Perseids result. Ideally, you need to have a look for them in the early hours of the morning, maybe between 2 and 3, but the moon will interfere at that time. If you're not an early morning person like me, you can watch from around 11 o'clock or so, when it is definitely getting darker, because Perseus is well up by that time. Now, the peak of the Perseids is going to be between 10 o'clock in the morning and 1 o'clock in the afternoon on the 12th of August. Of course, that's not much good for us. So people in Europe have been advised to watch for the Perseids on the night of the 11th to 12th of August, and then again on the 12th to 13th of August. You look for the double cluster. How do we find that? Well, we find Cassiopeia, which is very easy to find in the sky at the moment. And then we use these two stars, follow them down, and they will come to the double cluster. So if you look here, there is Cassiopeia. These are the two stars. There's the double cluster. And there is the radiant. Now, this is the area from which the meteors seem to emanate. So if you lie back on your deck chair and just look in that general direction of the sky, making sure that you block out any light of any kind, then you should get a good view. The moon will rise at around 11:30 on the 11th, and then about 12:30 on the 12th, 13th. Here we have the double cluster photographed by Dave last night. I was quite surprised at how clear it was last night. It was unexpected. So I'm going to show you some of the other. There are lots of photographs and they are all brilliant. The first 4 photographs of noctilucent clouds are by Neil Weston of Aberdeen Astronomical Society. Now, he did send them to me to be shown last month, but due to circumstances, it didn't work out. And but never mind, because we have the pleasure of seeing them tonight. And these are just beautiful. Here we've got wonderful filaments in amongst a sky that's full of different kinds of clouds. I love this one because here we have windmills, and of course with long exposure we have the fan shaped of the blades, and it's just gorgeous in amongst the filaments of noctilucent clouds here. Those were on the 12th of August, and on the 22nd Neil photographed these here, and my favorite, I think, these absolutely delicate strands of noctilucent cloud. Now, I was in Gloucestershire and saw noctilucent clouds on the 21st, 22nd. And although I know they can extend that far south, that's actually the first time I've ever seen them down there. So I believe there was a particularly good display that night. And then we have some wonderful noctilucent clouds by Sue Shackleton of North-Rollesay Astronomy Group. And again, composed beautifully. And look at all this gorgeous tropospheric cloud in amongst the noctilucents. And of course, Dave has to go one step better, because not only does he have the noctilucents, he has got the comet. And it must have been around the time when I saw it, because I remember seeing these two stars here. So that's just a fabulous photograph. And of course, we've got more photographs of Comet Neowise by Dave. This is one by Eric, very atmospheric. And this is Michael O'Donnell from Sigma. And Sue Shackleton, which is fantastic. And another one by Dave. These are really tremendous photographs. And here we've got the Moon, Saturn and Jupiter by Sue Shackleton. We have got Jupiter with the 4 moons by Sue. This is on the 7th. Now the moons move around Jupiter extremely quickly. So Michael's photograph was on the 13th, that's a week later, and you can see that they're in a different position. And then here, they changed again. So this will be a couple of weeks later. And this is a photograph of Jupiter and its moons by Dave. This is the Moon and Venus, a lovely crescent moon with Venus. So this will be a morning photograph by Sue Shackleton. We've got the Moon and Mars by Michael. And again, the Moon and Mars by Jacqueline. Now, Jacqueline, if you are here, can you let us know through the chat button which club you are affiliated with, please? Because it's something that we don't know. And this is, and I'm going to make a quick aside, because of course, with Mars reaching opposition and its closest point to Earth, this is when space agencies go absolutely berserk and start sending out spacecraft after spacecraft to Mars. So the HOPE satellite was launched by the United Arab Emirates. This is their first satellite. It went on board a Japanese rocket, and it should reach Mars in February of next year. It's going to be looking at the climate and atmosphere of Mars. So it's going to complement MAVEN, which is in orbit around Mars at the moment. And we have Tianwen-1, launched by China, which consists of a satellite and a rover. And my goodness, they've got ambitious plans, because when this arrives in April the 23rd, they are going to be hunting for past and present life. So it'll be interesting to see what they find. They're going to land, or the rover will land in Utopia Planitia. And this is quite an area of interest at the moment. This is Elysium Mons. And this tiny crater here with this lump in the middle, that's Gale crater, where Curiosity is exploring. Now, NASA, of course, has also launched a spacecraft. This is going to be a rover called Perseverance, and it'll land in Jezero crater. And notice the similarity to Curiosity. This has been a great rover. It's so that why change what's working well? So there are a few more bells and whistles. And of course, one thing that they have done is to make the wheels a lot better. Curiosity's wheels are just gradually being pierced by the very sharp surface. Perseverance will be drilling a couple of meters into the ground. It's then going to take the sample, put it in a safe place. It's never a good idea to put anything in a safe place, because you're bound to lose it. Because what should happen after that is that a spacecraft will come along, pick it up, take it back to Earth, where it'll be analyzed in laboratories. But what I like best is this. Look at this. This is going to be a little helicopter called Ingenuity. Now, it's got to be extremely light. The propeller blades have to spin incredibly fast because of the thin Martian atmosphere. So it'll be really interesting to see whether or not it actually works. And Perseverance will be looking for past life, hoping to find microbial life, as well as a few other things. This is Jezero crater, and immediately you can see why they want to send it there. River with a delta. So a delta, of course, is laid down. This is all the sediment that is brought in by the river and ends up in a standing body of water. The colors show minerals, and we know that there are clays there. So there must be, that means this is a really good place to hunt for microbial life, past life, but could be present too. Back to the photographs, and we have the International Space Station, photographed by Jacqueline, which is very good. I never managed to capture the ISS. This is probably my most favorite photograph. the crescent moon. It's waning, it's in the morning, taken by Dave Davidson on the 19th of July. And then I managed to get the to photograph the waxing moon. So this is a new moon, and that was 4 days later. Note the part of the moon that's facing the sun, because books and all sorts of things always get that wrong. So you know it's not real if they get if it's facing the wrong way. Almost at the end of the photographs, we have Dave showing us a new sunspot on the sun. Hopefully, this is the end of solar minimum. This is a white light filter, and we're looking at the photosphere, whereas the same sunspot taken a little bit later by Eric is with a hydrogen alpha filter. So we're looking at the lower part of the sun's atmosphere, the chromosphere, and you can see how different it looks, but the detail is absolutely extraordinary. And there was an enormous prominence to which we were alerted by Anthony, so thank you, Anthony, for that. And Eric managed to capture it, which is absolutely brilliant. Now, gosh, the Ring Nebula. Whenever I see the Ring Nebula, it conjures up images of autumn. But this is a fabulous picture by Dave. And I am showing the Soul Nebula by Eric once again, because this was chosen as a picture of the week by the British Astronomical Association. So well done, Eric. Here we go.
Pauline, thank you very much. There is nothing like a technical hitch to get the adrenaline going. But oh yeah, absolutely fantastic presentation. You've just given me a whole list of things I need to try and observe this month. So thanks very much for that. Right, we're nearly at the close of play tonight. So I have got time to take any questions about the club, a minute or two to do that. So if anyone has anything, just put them in the Q&A or chat, and Paul will probably pick them up.
Nothing at the moment, Eric.
Okay. Well, again, thank you very much for attending our monthly club meeting tonight. It was absolutely fascinating. I thoroughly enjoyed it. The time just seemed to flow. So, until next month, thank you for watching. Goodbye. We'll see you again.